Welcome to the 19th video of this course on quantum processing. Hopefully the cell phone is not processing. Okay, so last time we covered the superfluid multi-insulator case for quantum transition, which was a nice step beginning for quantum simulation of ultra-cold atoms and optical lattices. This time we will cover some of the thermodynamics of the Hubbard model, the Bose-Hubbard model that we saw in last video. The thermodynamics of this part is interesting, we will see it, but let's just remind ourselves of the wave functions corresponding to the superfluid case and multi-insulating case for the difference between the summation and the product sum of the creation operators on different lattice sides. Remember that the interaction energy is huge in terms of the kinetic energy. That's why you can trap particles per lattices or per lattice sides. We would like to say that the U is very big, so it goes to infinity. This is a good approach to study the thermodynamics at the atomistic level, and the kinetic energy is hugely suppressed. We would like to calculate some basic thermodynamics. Let's say that we would like to calculate the ground canonical partition function for the atomic system. So you would just product sum this for different on-site partition function, which is scaling for number of atoms. This way, this is the on-site partition function recovering the grand canonical partition function. Remember that this is the mu, this is the chemical potential at the lattice on side R, okay, the lattice side R. And what we would like to measure, or what we would like to extract afterwards, is the probability of getting or of finding number of atoms and the number of atoms here, okay, per lattice sides on the optical lattice. So you just get this well-known result of the probability distribution here. Remember that we have a single band interaction. This is the more dominant term of the Hamiltonian. This is the more dominant term of the Hamiltonian relative to the interaction that we can neglect. We just have the chemical potential and the single band of the on-site interaction energy that we can have. Here, we would consider the problem as a 2D radially symmetric problem of harmonic trapping potential, okay? And we would like to calculate the average density at radial r here. And to do that, you have to make sure that you sum for all the occupation states on the on-site partition function, okay? And this is how we can do that. Let's go to what experiments actually shows when we would like to measure these things. Here you want to measure the detected occupation density, occupation number. This is the detected N in the by using the fluorescence. You fluoresce light on the atoms on the optical lattices. This is clear, yeah. And then you can sum for all. This is what we call the parity projection problem here. Why is parity projection? You will see why we actually associate this term here. We just sum for all the densities here for the number of atoms and measured occupation, and you can see that if I have the odd occupation, the odd occupation actually is what survives during the measurement operation, and I will show you now why it does happen. Let me remind you, or let me just tell you something about the fluorescence. It happens at about 60 kilohertz number of fluorescence per atom, or rate of fluorescence per atom, fluorescence rate per atom. So also one thing also, which is that the holding the atoms actually in millisecond scale, so maybe hundreds of milliseconds, maybe say 800 milliseconds or something, and then you can calculate here the projection of the parity projection. The parity projection is what's actually intriguing for this kind of experiments, that due to the parity projection you can get the average number here for the detected density, which is nothing else than the squared of the density here for the occupation for R here. So one thing also, which is the uncertainty during the fluctuations or the measured variance that you can recover, that you take just the square root for the detected densities for both the squared and the other non-square here case. So we will only detect the parity of the on-site particle number. So you have particle numbers on a lattice and you will take the parity projection. What does it mean here? It does mean the following. This graph just summarizes what I say. So if you have light-induced collision, this is the density distribution of the particles on the lattice sides. And if you induce light, you make light interact, actually what you measure for one particle per lattice side is one particle per lattice side. But if you have two, the parity here that I mentioned for this term, if you have two, you measure nothing. This is the associated mod n for 2 that you can see. And if you have 3, you measure 1. So number of parity, number of odd number of atoms, you can get actually Poissonian distribution of the probability here. And this probability for the detected average density or the measured occupation density here is actually, as you see, is a following the Poisson distribution here for the mean number. If you can see that, sorry. For the mean number of n, and here the measured for the occupation density or occupation number of particles in the parity projection state here. So it follows exactly what I said, the Poissonian distribution. This is the problem, this is the probability for this number of atoms that you can have during the fluorescence. And what's interesting here that this is the experiment. So here the experimental effect of this thermodynamics of the system, that you can just get, as I said, for each lattice site parity projected algorithm constructed on the image, and you can see that even more fancy in images in any textbook of advanced topic of this condensed matter problem using optical lattices. You can go to this book this is the Anderson-Oberg book for quantum information and coherence. You go to chapter 2 and you see these nice images for parity projected measurements, and you can also see many images constructed for this Bose-Einstein condensate and superfluid case on real time. Thanks a lot for watching, and see you in the next video.